I have been in industry this from last 15 years, and my area of expertise is basically board bring up, writing Linux device driver, kernel programming, and then so basically I involve into network device bring up like gateways, switches, routers, and all. So I got an opportunity to work with VxWorks, Linux, Cisco iOS, Juniper operating system that is called as a JuneOS, and then I'm currently involved with the Linux as an operating system. Okay, so this is what about myself. So basically, we are going to talk in next 1.5 hours. What we are going to do is we are going to talk about the ELF. I know you all would be familiar with this, but we are going to bring some new things why we need ELF, what this ELF file format content is, and if we are going to modify here and there, what would be the impact of this. Okay. So any questions about the session if you have, or if you have any question in between, please feel free to stop me and you can have your doubt, or we can take the question and answer after the session as well. Depends on your reviews. Okay. So just a quick introduction about yourself. Jack Frost. I can see somebody who is Jack Frost. Can you please just have a quick introduction about yourself? Jack, able to hear me? Javier and Babu, anyone?
Yeah, I can hear you. I can continue. Morning. My name is Javier. I'm from Argentina, Buenos Aires, but currently living in Toulouse. Do you hear me?
Yes, we can hear you,
Okay.
Javier.
Yeah, great. So, well, I've been working with programming and IoT stuff and, Arduino, uh, building things with build product, device driver programming, and but mainly embedded systems, not like kernel programming and so on. And just would like to know more about this. And I really love the Linux way of thinking. So that's why I'm here, just to learn more. Thank you very much.
Yeah, thank you, Javier. Jack, anyone who wants to take next? And Babu, Rahul.
Hi, this is Satish. Um, I mostly work in some of these board bring up area as well, both in the pre-silicon and the post-silicon phase. I'm mostly now working in the option ROM space, option ROM drivers for the storage and the HBA controllers.
Yeah, thank you, Javier.
Yeah.
Next, can we please have a quick, and then we can start quickly. Rahul, Rohan, Varun.
Yeah, hi, this is Rohan here. I'm from Pune and I work at Veritas. So I've been working in file systems from last 10, 11 years. And yeah, this is very much interested. I'm very much interested in anything related to systems programming. So yeah, so this is my first time I'm attending this meetup.
Thank you, Rohan. Okay, anyone wants to take, then otherwise we can start. Okay, so let's start. If you want to put a message about yourself, that is also fine. So let's not spend a lot of time here and then start. So, so what we are going to talk about this. So the agenda of this meeting is we are going to talk about ELF file type, program headers, section headers. These headers will be coming along with your ELF. Okay, so no need to worry about. And then symbol, relocation, and dynamic linking. So let's make this session very interactive. I mean, what I do basically in all my session is I used to have a conversation with all of us, and then we can take further from that. So what do you mean by ELF? I don't have theoretical stuff here. So what I will be doing is I will be walking through the codes. We will be writing few programs, application side as well as the kernel side, and then we'll take it from there place. Okay. So what is ELF? Any thought? Anyone? It's fine. At least if you can speak or give some 2 or 3 words about ELF, that will be.
So,
What do you know by ELF?
so ELF, I think, is a format for executable. And the reason we need that format is someone has to get all the text region and everything from an executable and load it into memory. And then a process can be made out of it to run. So that is why we need some kind of known format, and that purpose ELF serves.
Okay.
Yeah,
Thank you.
for me, I really don't know the difference between ELF and binary formats, but I know that I need an ELF to do some debugging using GDB, for example.
Okay.
But
Any other thought? Any other guess? Okay. Anyone else wants to bring something?
Is it like just this file gives actually the mapping of the code into the processor address space? Is it the right statement to make?
Yes, ELF does a lot of things. Yeah, so this is one of basically what Rohan has spoken about, that the different segment which we have, right? Program segment,
Yeah.
basically.
Yeah.
So that is one aspect of the ELF, but there are the other aspects as well. Okay. What else? Okay, so I'm going to ask a question, very basic question. Okay. Let's say that you are writing a C program. Okay. Very any program. I mean, say you have just written a small program, C program. You have written this in one of your machine which you are working or which you are using for the development. Is that program will be, we will be able to run the same program on other machine as well? The same, or I will put the question in another way. The same
no,
program can be run in other machine?
it depends of the architecture.
Yes. So one is architecture. Yes. Very. What about the other things? So we brought one aspect is architecture. That's fine.
Yeah, the system you are running the application in. I mean, it's not going to be the same if you are running on Linux and, for example, on Windows. It's not the
Yes.
same
Yes.
ABI.
ABI, correct. So OS, we'll take another aspect is OS. Okay. What else? Okay, fine. We will take a look. Okay. So basically ELF stands, the name itself is saying is executable and linking format, right? So if you take a look at the executable files, right? I mean, basically the format will be used for executable files, object files, and libraries. I will talk about why I'm talking about the libraries. Libraries like a shared libraries. Okay. So as we highlighted here, like the same C program cannot be run on different machines. I mean, depends. If your machine architecture OS is same, then your program will be happy. If you are going to run the program which you have written, or say you have generated an ELF file, right? And the ELF file which you are going to port into some other machine, it may or may not run, depends on the environment of that machine. If the environment is matching where you have compiled your program and the machine where you are going to run, then it is perfectly fine. But environment is going to get differ. Environment, when I'm talking about the environment, it may be your OS, it may be AVI, it may be basically the architecture. So so it's not a portable, right? So it's not a portable one. That means you cannot port your program from one machine to other machine. It depends on certain criteria. Okay. And where your ELF plays an important role. Okay. So for an example, let's say that if I'm going to say here, say we all know that, right? So let's say that ls. Okay. Ls is what? Ls is a, what is this? Ls is a utility, right? We all know that ls is a utility. And if I'm going to say that, say which ls is going to talk that, okay, it is inside user bin ls. Now let's see the file format of this user bin ls. Okay, is saying that, so this ls is an ELF, right? Executable linking file format. And this is talking about the 64-bit. And this is LSB, shared object. This is your architecture. The current architecture is x86 64. SysB, it is dynamically linked. So these are the details about your utility here. Okay. This may vary from system to system. If you're going to run, it may be if you are having an ARM system, or sorry, are going to have some different architecture, power PC and all, right? This output would be default. Okay. So what does it mean is this file ls is a utility here. I mean, basically, if you're going to write a program, and I mean, we'll write a program and then we'll see that. So if you generate an ELF, so basically, okay, so let me, before coming to the ELF, let's talk about the different stages of a program. When you compile a program, there are the different stages, right? It goes through. So what are the different stages basically? Before it generates an ELF, there are some stages, right? So when you write a C code, then finally, before generating an ELF, what are the things happens? Any guess?
Yeah, you need the pre-compiling, the
Yes.
macros and everything. Then you need to create the object and then link between objects to finally make the executable.
Yes, yes. So the different stages of the program is like it will be going through the pre-processing, right? Compilation, then assembler, and then finally it will be basically coming to your ELF, right?
Linking. Oh, yeah.
Linking, yes. So ELF is, I mean, what happens is like if you have multiple files, right? Multiple datos file. Let me talk about the datos, object file, right? So multiple datos file, if you're going to combine that all datos, right? I mean, and then combining all the datos, you will be getting an output file, right? So that output file, which is basically which you are going to name, or by default, if we, I mean, by the way, if we are not going to provide an output file, the Linux or the Unix, right? It is a.out. You all know that, right? So what is the difference between a.out and ELF? Any
I
difference
guess
is
that
there?
the header and information you have about the program?
Yes, yes, perfectly fine. So the difference between a.out is basically if you are going to write a program, say vm hello.c, say include, then say if I will just keep this gcc hello.c, what will happen?
Uh, it will create the a dot out.
Yes, it's going to create a.out, right? And this file a.out, if I mean, let's see that whether it has created a.out or not. Yes, it has created a.out. If I'm going to talk about a.out, this is also saying that, see, that name is a.out. By default, if you are not going to specify any output name here, it is going to give you a.out. So this a.out is again an elf file which is having these attributes. Okay, I'll talk about this header details. So what happens is, like, when you are going to, okay, let's talk about few things here. If I'm going to say, let's put a hexa dump of this hd hyphen n64 byte. I'm going to get this information from a.out. So this 64 byte information, if you, I mean, I will be talking about more details about this. So this is the dump, hexa dump, okay, of basically, so if you take a look, this has some numeric value, right? So this numeric value I will be talking about, this is what your basically the ELF content is. Okay, so if you want to dump, say, if you want to dump some, say, 128 bytes, so this content is nothing but this content, or the hexa numeric value is going to tell the what kind of your header is, what kind of your architecture, okay, what kind of your OS is, what kind, I mean, is it a 32-bit application or it is a 64-bit application, in the ELF basically. Okay, this is what we are going to talk. Okay, so let me just go through the slides as well. By the way, where we use it, ELF covers object files, .os, shared libraries. I talked about, and it is also used for loadable kernel modules. Loadable kernel modules. After some time, we are going to write a kernel module, and then we'll insert it, and then we'll see that, or how the ELF look like. Okay, so we'll compare our user space and the kernel space, and we'll see how is there any difference in this ELF header or what is there. Okay, so ELF has at least two headers. Okay, so these are the basically from the code perspective I have written. If anyone, I mean, we'll be walking through the code as well. So ELF header, the first one is ELF header, and it has a program header. Program header is basically the header where we will be, I will talk about. So if you take a look at the layout of ELF, these are the two view of your ELF layout. Okay, one is the linking view. Linking view is basically, what is the linking view here? Any guess? Any idea? What is the difference between linking view and execution view?
I think the linking view might refer to shareable objects. You need to link it dynamically.
Yes. So linking view is, execution view is something like, linking view is, if I will tell in a high level term, it's a static one. Okay, execution view is the dynamic one. So linking view is a static. Basically, when you are building your ELF, that time execution view is like when you have a when multiple dots combined together, and then finally when you are going to build an ELF file, it will be look like this. So it program header, basically the linking view, you may not see the program header here. Okay, you may not see that. This is kind of an optional here, but when it comes to the execution view, program header will be mandatory there. Okay, so this is one difference. If I will go to the coding, I mean, let me open the code as well so that we will walk through the code as well. If I'm not wrong, it is inside next elf.h. Okay, so we are here, and then yes. So if we take a look at the header, right? I mean, I'm going to talk about, we'll write a program and then we'll walk through the header as well. Okay. So what we are going to do is, so this linking view and execution view, okay, by the way, sorry. So the linking view and execution view, is any doubt in these two, linking view and execution view? Any question?
Okay, one question, maybe a bit out of context, but why do we need a OS specific file format like this and a specific version for this for a specific processor architecture, of course?
Sorry, I mean, there was a little bit noise. Can you please repeat the question?
Yeah. So maybe it's so for a specific processor.
Okay, for the specific processor.
Could you write down the question, maybe?
Yes, that would be good. Yeah.
I wasn't able to hear it either.
Okay, so before there, let's talk about the user space, and then we'll take it to question. I think once we'll start with the programming, I think most of the question will be, I mean, it will be help to, most of the question will be answered. Okay, so what we're going to do is we're going to say, let me create a test.c file, and then probably we'll write this. So I'm going to write, let's write a function as well, int add, which is going to accept two integer int b, and what it is going to do is it's going to say, I'm going to say that printf adding two numbers, and say simply return a plus b. And coming down to the main, int main, say you have take two variable, a b equals to 10, b equals to say some 20 or any number, and then say, I'm going to say that, or what you do is just say that printf %d plus %d. return 0. Okay. Okay, so the very simple program which we have written, there is a function and there are the two variables which we are passing, and then it's going to sum up the two variables and returning the result. Okay, now let's compile this. We'll take this program gcc test.c -o test. So we have given a name here, so we are not going with the default a.out. What you're going to do, we have something. Okay, to few arguments to function add something. I missed it.
Yeah, it's
Okay, sorry, it's
comma B.
A comma B.
Yeah, the question is waiting for you in the chat. In the chat view. I already answered, but I don't know if it's the...
Why do we need a OS specific file format for a processor architecture? So, okay, so two things here, right? One is, if you take a look at the processor, right, the low level things, right, it's basically the architecture, right? So architecture, if we take a look at the system calls, let's take an example of the system call, right? How your system call works. System call will be one of the example which we can take. So it's like, if you are calling basically if you are calling a system call from your user space application, then what happens? Finally, right, it is basically your glibc. What it does is, it's basically it will break the instruction into the processor space. For an example, if you are taking if we are taking x86 architecture, so what it does is basically it is going to switch the application, or it is going to switch from the user space to the kernel space, right? And for that, what we do is basically there is a int0x80, right? In decimal it is a 128. 128 is for the syscall handler, right? So it is a kind of a software interrupt which is basically used to used for your syscall handler. And coming down, so this is where basically your architecture or the OS comes into the picture. Okay, so every architecture has their own instruction set. If I will go to the assembly, right, basically the instruction set, which the kind of a registers where you are going to move content of one register, move, compare, exchange, subtract, add, jump, right? So these are the instructions which will not be same from one architecture to the other architecture. Okay, that is why basically your question is, why do we need a OS specific file format for a processor architecture? So this is where you're basically the things get differ. Okay, now if you are going to run, say, if you're going to call or if you're going to run a program which has a system call and you have compiled in Linux environment, and if you are going to run into FreeBSD environment, FreeBSD is it's a little bit different from the Linux, right? It's not going to happen. It's not going to work there, right? Because the ABI, the instruction set will be different there. Okay, so that is your OS and architecture combining. It combines together, and then it's playing an important role here. Okay.
So Abhay, one question here is ABI. It's actually the processor vendor will provide you, right? Or it's it's depending on the OS.
Yes. No, it's a so two things. It's a processor vendor plus the OS as well.
Oh. Okay.
So say if I'm going to run, so for an example, let's take a GNU library, right? GCC
Right.
toolchain, right? So GCC toolchain will be differ for your Linux, and the same GCC toolchain will not be similar in your FreeBSD environment, right? FreeBSD.
Yeah,
or if you are going to take a, say, HP they have their own operating system, right? HP Unix.
Okay.
So the same GCC will not be working there, right? So this is where your basically the ABI will be getting differed based on your OS, based on your architecture.
Okay, so it's a mix of processor as well as OS. That's what
Correct. Correct.
Okay.
So let's run this. So okay, I hope this should be happy now. Okay. Now, if we notice here, we have test created, and this nature of this file is a utility basically, which is I mean basically we'll be able to see the type of the file. If I'm saying that say test.c, it will not be a ELF based file. It's an ASCII text, right? But if you take a look at the file which we have generated here, test, which is not an ordinary file, it is. And basically if you try to open this file, you may not be able to see this because this is not a text based file, right? See, right? So what we are going to do is we sometimes back we have used this hd dump. Now I'm going to say dump this, say let's dump 64 byte header information for this. So we're going to see that the same here, 7f. I will talk about the 7f and all. Let me dump the readable format of this, because this will not be able to understand this hexanumeric value. Okay, so what I'm going to do is I'm going to say, so there is a something called read Dlf utility. Okay, so if you just say that read Dlf hyphen header and then test. Now it is little bit readable in readable format. So what it is going to see, you're going to see the ELF header information, right? You're going to see the ELF header information, and this ELF header information is like, if you see the ASCII code, right? The magic header, the magic basically, the magic colon 7f. What is 7f here? So 7f is an ASCII code which is basically able to tell you that 45. If you decode the 45, it is, I mean, this is kind of a ASCII value of E, 4C, L, 46 is F, right?
Yeah.
So this is going to, so this is looking at this, this 4 bytes is going to tell you that it is an ELF. Okay, and this is basically the 7F is kind of a signature for this. Now, if you take a look at the class, I will talk about this 0, 2, and 1. What is 0, 2? Any guess, anyone?
I mean, 64 or 32 bit.
Yes, yes. So it says 64 or 32 bit. 0, 1 is?
It's saying that two's complement.
Yes, yes,
Little Indian.
yes. So I mean, a lot of things are there, right? So it's I mean, I talked about architecture, OS, but there is another thing here. If you take a look at the how you are going to store the data, right, into the memory, is this is also a part of your ELF. So your ELF is going to tell you that it is a two's complement, is a little Indian. If you are going to use say another architecture which is based on say big Indian, you may be able to see that the data is basically the big Indian. Okay, class is basically this ELF is getting generated for 64-bit architecture. That is why the ELF 64. If you are, I mean, if we compile the same program in a, say if I'm going to compile the program in a 32-bit architecture, say 32, 32. Now, let me open this test 32. The test 32, if you just see this, right? See the header information. If you, I mean, if we compare 64 and 32, it is saying that ELF is 32, whereas ELF is 64, right? Machine indexes will be same because I have compiled. I mean, basically we have built this ELF on the same machine, so it is same. Now, what else? If you see the OS ABI, right? The OS ABI is a system file. The ABI information it is giving that it is using as a system file. Now, what else it is? Type. The type is important here, right? It is talking about dynamic. The type could be multiple. Okay, so what could be the type? Shared object file. Why it is giving as a shared object file? Any idea?
Because you are using printf, and printf is a libc function,
Mhm.
and you need to dynamic
If you
to link
see,
the.
if you see the file, right? I mean, if I will just say the file test, it is also saying that it is a dynamically linked. Linked with what? This is dependent on this. Okay, this is dependent on this. What is this? LD stands for what?
Order.
Yes. So this is a shared object, right? And this is where, if you see, this is dependent on, somebody has asked that how the architecture and the OS will be. Here it is, if you see, there is a shared object file which it is getting used, and this is the architecture dependent shared object file, right? If, for an example, if you are running ARM, or say, if I will just say that file test32, you can see here, this is getting changed, right? So this is sitting inside your lib64, whereas this is sitting inside your lib32, is simply lib ld linux. Here it is ld linux x86. So coming back to the header, it is like, so this, the type of header would be difference here. The type of header, if you just go ahead and take a look at the ELF 64-bit header. So there is a, see, if you, I mean, we have dumped this header information, and what we are looking, the code is, it is the magic number, right? The magic number is what we have seen here. The magic number is this. How many bytes it is? If you take a look, I think I indent in 16 bytes, if I'm not wrong. And then E type, this is going to be the type here somewhere. It is a dynamic shared object, or it is a relocatable object, right? E machines, what kind of machines you have, version. P entry, these are the details which I have covered in my slides as well. So if somebody wants to take a look, what, I mean, basically, if you take a look at here, the comment is not, I mean, only mentioned for a few of the members here. Okay. So here it is like object file version, entry point, virtual address. So this is what we are going to take a look. Okay. Now the header information will have this many members, and these members, what we are seeing here inside the code, it is dumped here. If you take a look at the machine, is your x86 version is entry point address. It has dumped here 1080. A starting of program headers 64 byte into file. A start of section headers. Section headers we have not talked about. I mean, we'll talk about the section header as well. And size of this header is 64 bytes. Size of the program header is 56 bytes. So all this information you can get it from this ELF header. Okay. Now this will be differed. I mean, basically, if you compare 32-bit and 64-bit, there will be slight differ. Okay, slight difference would be there. So if you see that entry point, section header will also be differed here, right? Say section header is here 14784 byte, but here it is 14400 bytes. Okay, so these are the details, which is basically it is now let me, so this is a basically this is a shared object based file. Let me run a program and generate a .o file, and that .o, what we are going to use, I mean, we are going to dump, or we are going to use our read Dlf utility and dump the ELF header and see that if we are not going to generate, because ELF will be also applicable for your .os. Okay, so now gcc test.c, I want to generate a file set test.o. I have just given. Okay, ls So test.o got generated. Now the file format of test.o, if you take a look, this is where it's giving a very minimal information, right? If you see, it's not giving this kind of a dynamically linked interpreter. Is this? It's just saying that it is an ELF 64-bit LSB and relocatable. This is an important piece here. This is a relocatable. What is relocatable? Anyone? What is relocatable? Why we are not seeing a relocatable in final ELF?
Might it be the sections that you can move them in memory? It's like they are relative offsets
Yes,
instead
yes,
of
yes.
fixed offset.
No, if you just dump this, right? For an example, if I will say that obj dump, right? For that I have to test dot. Let me redirect to test o dot file. -d. I will open this, right? I will just highlight you what is the difference here, okay? So if you see the offset here, right? What he was talking about, the offset, you are seeing the 00 here, right? So the section, right? De-assembly of the section. This is a section header. We are taking a look. The section header, this is an offset. If you see, the main offset is here, but the add function is basically we are not able to see any offset there, right? So these are the instructions which has been going to this .o file, right? Now, if I will say, if I will just go and say here, for example, let's say that test and remove this file, test underscore elf file, okay, underscore elf file. See, what is the function here for us? It is a add main. Let me see the main function. Be starting somewhere. Yes. Now, if I'll go here, the top of this add, if you see here, the earlier which I was talking about the test.o, it is a relocatable, means I need to basically, it is going to relocate. I mean, it is a relocatable. So it is not a final, and it is not a final ELF. What happens is like when your daughters get combined together and when it is going to make a final ELF, it is going to work with the offset and all that. Okay, which function, I mean, if there is a jump instruction is coming, where I need to jump, which instruction set I have to jump. So this is like, so if you take a look here, 1169, right? If you see here 1169, for example, say somewhere we will be calling as a add, where we have called it as a add somewhere. This is the main function, by the way. So call q 1169. Okay, call q 1169. 1169 is an offset where your add function is located. Okay, but this information, if you take a look at the previous one where in the .os, this kind of information will not be available. Okay, so if I'm just walk through the main, so if you just take a look at the main, call queue, okay, it just simply
It uses the relative jump,
yes,
the relative offset.
yes, correct. So it's not a permanent, I mean, basically it's a temporary things which it is using, but when your ELF will be getting ready, that is basically it try to resolve all the symbols. Symbols means it try to resolve all the offset, and then finally it make an ELF ready. So in ELF file, you can see you have a proper offset will be populated there, but whereas in Dotto, you will not have the offset, or few things will be included. Okay. Now let's back to the header. What we are talking about? We are talking about yeah. So this ELF header, right? So basically, this is going to be it's going to have multiple information, and here let me back to the slides. So it has the program header table entry size. Now ELF header, some important details with the ELF header. E underscore ident is initial magic bytes that provide an answer for the OS on how to interpret and decode the file contents. Okay. So any guess that how, I mean, for an example, let's talk about few, I mean, I little bit I'm diverting from the topic, okay, from the ELF. What happens when you load a program into the memory? Does ELF plays an important role there? How a program is getting loaded into memory? Any guess? No? When we say that, when I'm going to say that we have generated an ELF, right? ls-lrt. When I'm going to say that test, what is happening behind this? Any guess? ELF is coming in between? Yes, no? No? It is basically when you are going to say how this is a cell, right? If I will do this echo dollars, this is going to be a cell for us. This is basically a terminal, right? We have opened a terminal. Now in this terminal, we have a bash utility, right? This bash utility is what it is. I mean, basically, what is a cell, by the way? What is cell? No? Okay. So how this is loaded into memory? For example, let me just quickly do this. I will just modify this program so that we all will be able to see what is happening underneath. Otherwise, this program has terminated, so we'll not be able to capture more details. I want to basically add a statement here, get char. I want to stop this for user input. Okay. Now test.c -o test. Okay, now let us see that I'm going to run this test. Oh. Or you add something here is like, say, sleep for say 100 seconds. Okay, let me go back here and say that ps-af test. So this is the process ID which has created here. Now 14201. So here we are. Okay, so this is basically what I was talking about. Your program has been loaded into the memory. Now, if you take a look at these are the segments which has been created for your program, right? So here are the things. If you notice here, there is a heap, there is a stack, and there are few details here, right? So these are, if you notice here, these are the basically along with these, there are the shared library which is also getting loaded into memory, right? And these, not only this, libc, I was talking about the libc is basically which is going to help your program to talk to the OS or to talk to the kernel. There is a loader which is basically coming into picture. So what happens when you are going to load a program into the memory?
I guess that the OS calls the loader just to exactly load all the sections. I mean the data section into RAM, initialize the variable you need,
Okay.
set to 0 if you need some.
So the basic question here is like this program has terminated, right? Now, when I'm doing this test, who is helping this program? This we are, so first thing we need to understand is, we need to understand uh, when you are going to run this program on the test, there is a power fluctuation happens. 1 minute, just a minute. Able to see? All are able to see? Able to see?
To see what?
Able to see
Yeah,
the screen?
yeah.
Okay.
Yeah, the screen. Yeah.
Okay. So what happens is like, this is another program, right? My cell is a cell. I asked few, I asked sometimes back to what is, this is running here, echo dollar shell. So bash is a program where we are going to run our program, this dot test, slash test, right? So bash is helping this program test to load into the memory. So for this program, for test program, what will be the parent? Parent would be your bash. All are agree? We have not captured these details. We can give a try. That's so your parent will be your bash. Now, how you are going to? So there is a system call basically exec. Exec. All are familiar about the exec system call. Man to exec. So what happens with the exec is like, you are basically with the exec, you can do a man of this exec b. Exec b, what happens is this cell is what it is doing underneath, it is invoking a system call exec b. Exec b, it is loading this, one of the parameter into that call is this test. So this is one of the argument, and apart from that, it is also appending few arguments, okay, the permissions and all. So this, when it is going to do the exec, what it is going to do? Exec is basically, it is creating a child process, and that child process is going to get override by the address space of this, by basically the text segment, right? So this test we have seen, right? This test is containing a lot of information, lot of basically the instructions, and these instructions is going to be loaded into the memory. So when we have loaded into the memory, we have seen, so it is coming with this. This is what, this is your read permission, execute permission. So this is your text segment. This is going to be your so it is going to text segment, it will be bss, data segment, all will come, and then heap, and then so finally your you are going to see in the memory all the segment dump of your program. And if your program is dependent on some shared library, some other library, then that will be also getting loaded along with your program into the memory. That is what we are going to, what we have seen here, right? Now coming back to the topic which we are talking about. So here, so exec b is helping you. So this is going to be a child process, and the parent would be your shell. And this is this will internally does a lot of things. So where your ELF will be coming into the picture. What it does is basically, there are the functions which is going to, first it is going to read the ELF file. It is going to read, and it is going to match the environment where you are running. It is going to say that it is compatible with my current environment or not. So if it will be compatible with the current environment, then your program will be loaded into the memory. If it will not be compatible means when it is going and walking through your header, whatever the ELF header it has, once it will be happy, or once it will compare and see that, okay, my current environment and the ELF or the executable, whatever we are loading here, is basically the nature is matching, then it will load into the memory, and then you can see the header information into the memory. That are whatever the address which we have seen, by the way, the all are the virtual addresses. Okay, these are not the physical addresses. Okay, so let's go back now. We are running little bit late, so let me just go and highlight few things here. Now if we go and say the read elf -l test, see the offset it is talking about, right? The offset it is talking about, these are the virtual file size. And what are these, by the way? Any guess? So these are the headers. Okay, so these are the headers basically. So these headers are, how this header works is, if you take a look at the code which we have highlighted, so these are the header interpretation load where requesting. See, now if you take a look at the here, this is an important which I wanted to highlight. This is a this is basically a program interpreter. So program interpreter is nothing but, this is dependent on this shared object. So this lib64 loader -linux x86 64, this is also getting, and this is what you can see into the interpreter. Now if I will take this and use this .o, you may not be able to see the header there. No program headers in this file, because this is not a dynamic, or this is just a relocatable object. That is why you are not able to see any program headers in this file. Okay, when you're going to use this, if I'm going to use this with 32, you may see some different information. Okay. So this is how it happens basically. Okay, now coming back, so let's write a kernel module as well, and then we will talk about we'll compare the header, and then I will walk through the section header and all. So let me just ls let me say that hello.c is there. Hello 1.c include Linux module.h. This is for module programming. Now you are going to include a header file called Linux kernel.h, which we are going to include for the kernel related stuff, and then put Linux init.h. Include something happened. Let's see. Now let me just say that I'll make it very short. Not static int underscore init, and say that hello underscore start of the module. Basically this is going to say we are just adding, say, print k. This is just to display the message inside your loading module. This is okay. Let me just put a new line also, so that it will come into the new line. Then return 0. Return 0, simple. Then static void underscore exit is to, when you're going to remove the module, this will be getting called hello underscore end. This is going to be no argument, so we are going to just say that print k, then kern underscore info. This message we want to see on our screen, exiting, say just exiting hello module. Exiting hello module. And now I'm going to say that fine. So this is, so we have written this hello start, hello end. This is very minimal code. Now let me say that module init and module exit. Hello underscore start, and this is going to be module underscore exit hello underscore end. Okay, fine. We will, so now what I'm going to show you is, we have seen the header information in our ELF file. I mean, basically the ELF file for the user space. Let's see the information into the kernel module, whether what kind of information this kernel module is holding. Okay, so -rf hello.c. In order to avoid the confusion, move hello 1.c to hello.c. Okay, now we have to write a make file for this. So make file for this is going to be, say, vim make file, because we will not be able to run without make file. Now obj hyphen object hyphen aim equals to hello dot o. Hello is our .c file, all colon, say make hyphen c /lib /modules, and then what you have to do is you have to say the dollar and shell, we are going to take the name from the uname-r, what kind of repository it is using. Cell uname-r we have done, and so this will come, then slash build directory will go inside the build directory, and then m equals to dollar, take the current working directory, and then build the modules. Then we can come here, clean, then say make hyphen, I will just copy the paste. Make -c, all will be same. Only thing is, right here you have to, instead of modules, you have to make a clean. Okay, so now let us build this. Make okay, it looks like something we have missed this. Shell uname-r slash build slash m equals to $pwd $modules, make -c lib modules cell space for the problem. Okay, so what is going to happen is make -c lib modules $shell uname-r shell uname-r build-m build. Okay, this is build m equals to, this would be the space one. Okay. Okay, so we have built the module now. So what kind of source file we have? I mean, we have a, sorry, we are where, okay, we have written inside the, okay. So here we have got a final.ko file. I suppose to move this code inside the current module, but anyway. So we got a .ko file, right? Now, if we take a look at the hello.ko file, this is a relocatable. Okay, so this is not an ELF file, by the way. Okay, so this is not an ELF file. What it is going to do, it is, so when you're going to insert this file, right? How we are going to insert this file? We are going to insert this ins mode. And then if you're going to say that hello.ko sudo ins mode hello.ko the message loading module hello. Now, so let me just go through this. Now we are going to use the same read Dlf utility, and we are going to dump the header of this hello.ko. So this hello.ko, if you see whether it is a user space or kernel space, it's going to populate the header. The ELF header will be there, but the ELF header here, this the magic number which we have taken a look. This magic number will be same. Class is, it is also trying to figure it out whether this is a 32-bit or 64. 2 is complement, Little Indian. All information would be same. I mean, basically. So this is kind of an. Now, if we use here a -l option, it's not going to, because this is, there no any program header. So this is not a, basically this is a relocatable file. That is why it is giving you or provided a very less information here. Okay, so so basically you are not able to see any program headers. Why? Because it is an ELF file. So whether it is a kernel object or whether it is a user space object, you can see if you have compiled your program using GCC, you can see the read, basically you can see the ELF header. ELF header will be appended, and this ELF header will be helpful when we are going to insert this module inside kernel. This is, it is a type of a relocatable file, because I cannot go and insert, I mean the ELF, if I will be just loading an ELF here, it will be basically I have to use different methodology. Okay, so kernel objects are relocatable file. All the kernel objects are the dynamically module which we are inserting and removing, right? That are the relocatable files. We place this and then we once, so it basically, why it is, why I mean, how, if we are going to insert this module, there is no any dependency with other module. If there are the dependency, that then you have to resolve that dependency as well, and then only finally you will be able to, suppose for an example, if this module is dependent on some other module, right, then probably you need this to load that modules. So that how you are going to figure it out, there is a module order. Okay, so for example, we have written a very simple program, so module order will not be. But if your program is basically dependent on different modules, you can see the order of the module, and and you have to follow the order. So basically, one module you have to insert, and then the subsequent and the subsequent. So this is how your basically the relocatable works. Now coming back to, let me touch few slides. So the program headers describe segments within a binary and are necessary for program loading, which we have seen. These segments are understood by the kernel during load time and describe the memory layout of an executable on disk. So I have highlighted here, right? So this is how your program header will be. Basically, your program header will be helpful to do these things. Okay. Now, program headers do not exist in relocatable object, because these are the .os file and are meant to be linked into an executable, but not meant to be loaded directly into memory. So this will be applicable for user space, but in the kernel space, you can see that you can load the kernel object directly into the memory. Okay. Coming back to the program header, these are the program headers structure. I mean, the structure, remember, if you see the segment type, what are the segments? It is a text, it is a data, or it is a BSS, or it is a stack. Okay. Segment flags, whether it is a segment flags is like you, what kind of permission you are going to. Segment file offset, virtual address, segment physical address, segment size in file, what is the size, segment size in memory, segment alignment, file in memory. So these are the program headers attributes, and this will be basically when your program will be loaded into the memory, this information will be there. Now I may share this slide. I don't want to go through these slides. I just want to touch few things. There is a flag, there is a member call in ELF phop. Phop basically points to the start of the program header table. And phop is basically what happens is like when your program will be loaded into the memory. I mean, before loading to the memory, this is where it is points to the start of the program header table. So this is the first starting point of a program header table. And this is the size of one program header table. This phnum contains the number of entries into the program header table. So this is how your basically the program header looks like. The section header may be the section headers. Section headers is a section header table reference the location and size of these sections, and the section headers are not needed for correct program execution, whereas program headers are, which we have seen. So you can happily strip away section header. That is why in the figure which I highlighted, it was an optional. You can remove without a section header. Your program may be loaded into the memory and you can do the things. So it is kind of an optional. When taking a closer look at section, it appears each can hold code or data, for example, program data such as global variables or dynamic linking information that is necessary for the linker. So section header will be, what will happen is like if you have multiple daughters bringing into between, right, and combining that all, you are making a final executable. In that time, you can see that the section header will be populated for each daughters. The section header is like, again, these are the basically if you take a look at the code, here comes, let me go back to the code. ELF64 underscore SHDR. So here are the two pieces. Now, if you, sorry, this is not for us. So if you include, yes, so this will be user include Linux. So this is your header information. If you just walk through this, it is for the 32-bit, you have a different header. For 64-bit, you have a different header. Okay. And if you say, what are the version? So these are the magic numbers which we have taken a look. Okay, 7F, E flag, magic 1, magic 2, magic 3, right? This is what the class is basically, which these are the three classes which we have. Basically the 1, 2, for 32-bit, class is 32-bit or class is 64. Class num is, this class num will not be applicable basically. This is like a LSB, MSB, right? The version is like, version is none. And this is like, if you see this, ABI is Linux, ABI none. We are walking through the Linux code. So these are the information which you can see. Now, these are the architecture specific. If you take a look at the ARM, hardware, watch, break, so a lot of things are there. If you MIPS based, if you just take a look, the type would be basically, the main thing is the type. So the main thing is this type. So the type E machine, which is going to specify the what kind of hardware architecture if you have, right? These are the basically kind of a data type which they have typecasted as a ELF32 or ELF64. So I would request you just go through this header file. If you want to just say that where we are using this header in our code, then probably what we can do is we can just take a look, and then it will point to the file or the function from where we are parsing this header. Okay. Now Elf util.c. Okay. So this is, if you come here, this is like, is kind of a parsing the header. Okay. Parse ELF64. Now see that there the compare is equals to this, equals to this. Then it will come here. So it is basically going through and matching the headers, okay, the flags and all. And if machine is EMPPC64, so these are the basically which I was talking about. So this will be depends on the architecture. Okay. Now here again they are passing the header offset, and they are walking through all these things. Okay. So this function, if you, these are the files places which if you want to take a look, right, I will highlight you the there is the miscellaneous file. this miscellaneous, this is based on the architecture. There are file related to crash dump only anyway. Key exec file.c. This is basically for your crash prepare ELF64 headers. So if you're seeing one thing I just wanted to highlight here is like when a crash file is getting prepared, right, at that time your ELF header will be also playing an important role. Okay, so based on say basically if you take a look at the code, right, what it is doing is based on what kind of, it is a 64-bit or 32-bit, based on that it is going and preparing this the crash. Okay, this is mode post ELF header. This here are the things. Okay, so elf.c. So if you want to start, you can start from this place. No, this is for the testing one. Save and one tool testing. These files are basically, if you just take a look at what is happening, you can just path of the elf file, and then these are the elf load. So you can just walk through this. Or the other thing which I wanted to highlight is the miscellaneous is where parse elf. So this is architecture. Okay, so this is a risk architecture. Now module.c, no, so this is an important one. elf.c. Off.c is basically power pc. Okay, now there is a module.c. This is your power pc again. Okay, so these are the architecture specific code, right? How your architecture opens the header, what kind of field it is trying to look into that and matches. So all these things we can see it here. Now the crash dump things, right? If you say that this architecture is 390, okay, kernel crash dump. So it's a few architecture, basically they look for the header, and then before dumping them, I mean, they make sure that okay, I have to dump in this format. Okay, so vmcore.c, if you just come here, 0, this is also S39067. This is a file, this is a generic file. Okay, this is a generic file which is, so fs is a file system, the proc and the vm core. So this is I mean, this is basically your Linux use this. So copy elf node segments in a given buffer, and I mean, basically you can walk through this, so it does a lot of things. Okay, now so this is what the header informations and all. Yeah, finally we are running out of time, so I have to close this here. So yeah, any questions? So I would suggest you to just use this read Dlf utility. Read Dlf has a lot of things. Basically, if you just say that read the few utility, I will suggest to just go through help. It has a lot of things, like you can dump all the header, uh, I mean all headers, like it is a section program. If you want to just do the program headers, you can use this. If you just want to do dump of this, display the section headers, you can use this. Section groups, if multiple daughters are there. uh, Dynamic symbol table, if you want to just go, I mean, if you have a global variables and all, you can use some global variables and then use this, and you can see the differences. Okay, relocatable, if presence, you can just use this. The word, this is kind of a architecture specific, display architecture specific information, if any. So if I will be just using, say here, read elf-a and test. Oops. Hmm. It's not displaying. Okay, so basically few of the architecture they have this thing, so that you can see that if you just do a -a, it will be dumping all the information. So you can walk through this. Say basically you can see that from where your frame starts, data starts, right? Text starts. So all these things you can see that BSS start, main, right? So before that, I mean, if you just want to dump all the information, you can basically use this and say that. So if similar will be applicable for your 32-bit, it is like, say, this is a printf. So we have, I mean, this is a very minimal code which we have written. If you will just add a lot of code, you can see a lot of things here. Okay, so here if you see that the printf glibc, okay, puts, right, slip we have used. So slip is where slip is basically the whatever the library which we have used, we are able to see here. Okay, and it is basically it will tell you that what are the libraries you have used, and this library is part of glibc, or I mean what is the glibc version and all. So it is just it will display a lot of information. And shared library, say init, finally the shared library which I have shown you, right, that is loaded libc.so dot. So you can just walk through this. This is a very, I mean, brief information it is giving. The section headers, what is the section headers start, node GNU, this is build ABI tag, right? GNU has dynamic symbol, dynamic string, GNU versions, and all these things. It will basically RO data, read-only data, frame header. So this will basically dump all the information, and this information finally your program will be. So what happens is like loading any program to the memory, this information is required. If you are going to change or manipulate any of the information, your program will be not loaded into the memory. So that is why from the security perspective also it is important. Okay, so most of the people, what happens from the interview perspective, I will be talking, I will not take more than 2 to 3 minutes. From the interview perspective, if I mean in my previous batch, few of the students who had gone to for the Qualcomm interview, where they had asked few questions from the ELF, and they were talking about the same thing because they had not prepared the ELF things and all. So you have to, I mean, if you are, I mean, we cannot expect in interview that what kind of questions will be asked and which are the areas they are going to ask, right? So at least you should know the what is the header, what is the section header, what is the program header, where it is required, why it is required, right? So all these things, at least you should, I mean, those who are kind of interested into the hacking and all, for them, it is very much required. I mean, they need to understand in and out of the header, okay? Because the header is one where you are basically going to manipulate the things, okay? So yeah, that's what from my side. So I just, if you have any questions, we can take it. Otherwise, we will wind it up. Okay, so if you have any questions, what you can do is we have website. You can post your question uh, into this linuxkernelfoundation.com. Me or somebody, some other will get back to you with all the details. Okay, so let me see if any chat questions is there. Okay. So thank you all. If you don't have any question, then probably we'll wind it up.
Thanks, Abhay. Thanks.
Okay, so do we have access to your slides, Javier? Yes, I will share the slides. Hope if somebody, I mean, if I'm not sure if somebody has your email ID or not. If you have email ID, or if you can just post a query here with your email ID details, what I will do, I will just upload the slides there, and then probably you can get it from there. Okay. Any other question? Anyone? Yeah. So thank you all.
Thanks, Abhay. Thank you.
Yeah. Thank you. Bye.